Most of chapter 6 is about exponential functions and log functions. So this is where we start getting into it. And what an exponential function is, because we've seen things where the x is down here as the base, and then you have a number in the exponent, right? Like that's what polynomials are, right? X cubed, x squared, x to the fourth, right? We've had that. But now it's the other way. Now the x is in the exponent, and this a is a number, right? And a is going to be a positive number, and also a is not 1. Because if a is 1, this is boring, right? Because then you just get 1 all the time. It's just a constant function. But you don't get a constant function when a is anything else. So it's not going to be 1, but it's going to be positive. And this is at first kind of a weird thing if you haven't seen it before, just with the idea of having x in the exponent, right? Like that feels weird, just because we haven't really had it. Although it'll happen a lot in this chapter, so hopefully if you haven't seen it before, you'll get comfortable with it. But just first of all, like, what does the graph of this look like? Right, that seems like a reasonable question. Well, this would be the easiest base that I could pick to use, just because then that way the y coordinates don't get really huge. At least, well, they will, but just not right away. So I just plotted a few points, and if x is 0, you would have 2 raised to the power of 0, which is 1, right? If x is 1, 2 to the first power is 2. If x is 2, you get 2 squared, which is 4. And what about negatives? If x is negative 1, you get 2 raised to the power of negative 1, which you can rewrite with a positive exponent like this, right? It would be 1 over 2 to the first, which is 1 half. Or if x is negative 2, you could rewrite that as 1 over 2 squared, which is 1 fourth. All right, so then let's plot those. 0, 1's right there. There's 1, 2. Then there's 2, 4. And I guess you need to be kind of precise here because you don't have a lot of room, but that's supposed to be negative 1, 1 half, and then that's negative 2, 1 fourth. And you get this kind of shape because you can kind of tell looking at these points, there's no way you can get a negative value. There's also no way you could get 0, right? What number would you raise 2 to in order to get a 0, right? That doesn't even sound like it's possible, and it's not. But also, you can't get negatives, right? What you're going to get with big negative numbers is just values that are barely above 0, right? That's pretty much what happens. If x is negative 100, you're going to get 1 over 2 raised to the power of 100. That's a very tiny positive number. It's very, very slightly above the axis. So yeah, this is the shape that you're going to get on the left side. It's going to approach the x-axis. It'll get closer and closer and closer to it, but it's never going to touch it because there's no way to get f of x equal to 0 because there's no power you could raise 2 to in order to get 0 back out. The other option is what if your base is less than 1? Because just to scroll back up for a second, if instead of 2 to the x, you have like 3 to the x or 5 to the x or something like that, you get this general shape. It's just that like 5 to the x is going to be steeper than this because then instead of going through 1, 2, it goes through 1, 5. And instead of going through 2, 4, it goes through 2, 25. Right? Because then 5 squared is 25. So this gets a lot steeper, but it's still going to be this general shape. If you have a base, so like the base being the number that's down here, if you've got one that's less than 1, then you get the same kind of shape just facing the other way. Because then, I mean, you still have 0, 1 here because anything raised to the 0 power is going to be 1. So 0, 1 is always going to be part of that graph. But now if you raise this 1 half to any positive exponent, where you get 1 half to the first, 1 half squared, those are going to be little numbers, right? 1 half to the first is just 1 half squared is 1 fourth. So now with positive x values, you're going to get these little y values here that get closer and closer and closer to the axis but never touch it. And then if you have negatives, so like 1 half raised to the power of negative 1, you could distribute that and say, well, then that's 1 to the negative 1 over 2 to the negative 1, but if you reverse those, so it's written with positive exponents, it's 2 to the first over 1 to the first, which is 2. Then you do the same thing with a negative 2. You say, well, that would be 1 raised to the power of negative 2 over 2 to the negative 2. You could reverse, interchange those to get the expression written with positive exponents, and you'd have 2 squared over 1 squared, so that's 4 over 1, so that's 4. So when your base is less than 1, it's shaped this way, where then it's going to approach the x-axis on the right side, and the left side goes upward, like that. So kind of the reverse of what happens here, at least left to right, kind of the reverse, right? It looks like what's here in number 1 and what's here in number 2. It looks like if you reflected number 1 through the y-axis, you'd get number 2. And yeah, that's the idea. And that's because the bases are 2 and 1/2 that it works out like that. I guess the same thing would happen if you used like a 3 and a 1/3. But 2 and 1/2 seem like the easiest ones to graph. Another logical thing, if we've got exponential functions, it seems like we should probably also have exponential equations that we could solve. And we do. And there are a couple of different types, and our book uses type 1 and type 2 to differentiate them. So what our book calls type 1 is something like this, where the bases on both sides, or I guess you can manipulate either one side or both sides so they have the same base. So then when you rewrite it, either they both have base 2, or they both have base 10, or they both have base 5, or whatever. So something like this, that's what you're trying to do. You're trying to get it to where it's the same base on both sides. So this first one, you got a 3 on the right, and you think, okay, there's not a whole lot you can do with that. But on the left, 81, like, is there a way that you can raise 3 to a power and get 81? Yes, there is. It's 3 to the 4th. So you say, okay, well, 81 is 3 to the 4th. So this is 3 to the 4th raised to the power of x. But then you can say, well, then if you have a power to another power, you can multiply them together, right? So this is 3 raised to the power of 4x. And then the thing on the right, it's just 3, but we're eventually going to equate the exponents to each other. So I'm going to write this so it has an exponent in the expression. And 3 is the same thing as 3 to the first power, right? That's a weird way to write it, but you can. So then if 3 to the 4x equals 3 raised to the first power, then 4x has to be equal to 1. Right? If these expressions are the same, they have the same base, they have the same exponents too. But then if 4x equals 1, then that's pretty easy to solve. You divide both sides by 4, and then x is 1/4. The next one, we kind of do the same thing. And this is one where we got to rewrite both of them. So I would look at this and I would think, well, 1/4 you could write as 4 raised to the negative 1. And 64 is 4 cubed. So, okay, maybe we can do this with 4s, right? So there's the 4 cubed. And then the 1/4 is 4 to the negative 1, then that's raised to the power of x. So again, we're going to use this maneuver where if you have a power raised to another power, you can use that base and then the powers are multiplied together. So negative 1 times x gives you the negative x. But if 4 raised to the power of negative x is equal to 4 cubed, then negative x has to be equal to 3, and that means x is negative 3. There is an alternative for number 2, which is that you could use a base of 2 instead of a base of 4. I would not have seen it like this, but somebody might, so I figured it was worth bringing up. I would see the 4 right away, not the 2. But if you see it with the 2 right away, just if you think like that, where you can always reduce it down to the smallest possible base, I'm jealous of you, but I would not have seen it like that. But you can do it. So you would say, well then, 4 is 2 squared, so 1/4 must be 2 to the negative 2. And then 64 is 2 to the 6th. All right, well then we use that property of exponents here, and we end up with that negative 2x is equal to 6, so x is equal to negative 3. You would get the same answer either way, and I figured for completeness' sake it was worth throwing this in, because even though I think most people are probably going to see it with the 4s, if you can see it with the 2s as well, that's great, and that will still work. You'll get the same answer. With the next couple of examples, number 3 might actually be easier than number 2, because you don't have that negative exponent in there to worry about. And here it's pretty clear what's happening. Like this left one is already set up, right? It's got a base of 5. You think, I really can't do anything with that. It's a prime number. But then 25 is 5 squared. You know, oh, we got a base of 5 on both sides pretty quick then, right? So 5 raised to the power of 2x minus 1 equals 5 squared. So then the exponents must be equal. So 2x minus 1 has to be equal to 2. And if we solve that one, you add 1 to both sides, you end up here. Then you divide both sides by 2, you end up down here where x is equal to 3/2. So that one's actually not that bad. 4 is really short, but there's a thing that you have to see in order to get it to work, which is that anything raised to the 0 power is 1. Because looking at this, the 3 raised to the power of x plus 6 equals 1, you think, well, where's the other 3? Right? Because aren't we supposed to have the same base on both sides? But you have to rewrite 1 as 3 to the 0. And it's just using that idea that if you raise anything to the 0 power, you have to get 1. So you just use the base that matches up with the left side here, right? So if I use a 3, then everything matches up. So then x plus 6 has to be equal to 0, right? The two exponents would have to be the same. So then x would have to be equal to negative 6. Next example, number 5. E is a number. It's about 2.718 roughly, but it's also the base of natural log, which is the thing that shows up in this section. That's why E is showing up now. But if you look at this, you go, we've almost got both of these written with base E. It's just that we need to multiply this one out, right? We've got e to the 4th raised to the power of x, so we can write that as e to the 4x. Then we've got the two expressions equal to each other with the same base, so that means the exponents have got to be equal. So 3x plus 4 must be equal to 4x, which would then mean that if you subtract 3x from both sides, 4 would have to be equal to x. All right, so that one's just there because it throws in e, which makes it a little bit different, right? It feels a little bit less concrete if you're not used to using e, but e is just a number. And then over here with number 6, we've got to rearrange both of those, right? Because it's not like we got a prime number as either of those bases. So we're going to have to do rearranging on both sides, but both of those numbers, the 32 and the 16, they're both powers of 2. So 32 is 2 to the 5th. 16 is 2 to the 4th. And then on both sides, you've got power raised to a power, so you can multiply. So the left side is 2 raised to the power of 5x. The right side would be 2 raised to the power of 4 times the quantity 1 minus x. And then I just distributed the 4 and said, well, if you multiply those together, you'd get 4 minus 4x. But then, now that we've got the bases equal and those two expressions are equal, then the exponents got to be equal as well. So 5x would have to be equal to 4 minus 4x. You solve that, get the x's on the same side. You have 9x equals 4. Divide both sides by 9, you get that x is equal to 4/9. So for this sort of thing, I think for the type 1 equations, this is about as involved as they get right here, where you've got to manipulate both bases in order to get them to match up. So it's almost like you have to figure out in advance what base you're aiming for, where you're going to try to get the same one on both sides, and then go toward that. Rather than trying to like do one side and do the other side. So you got to sort of plot everything out in advance, I think. I think that works out a lot better here.